All right, here is a Biot-Savart application. This application is a straight wire of length L, and we're looking at 2 points of interest here. One is on the perpendicular bisector of the wire, some distance away from the wire, and the other is just some distance off to one of the ends of the wire. So these are both important applications to understand, and we'll take them on one at a time. I'm going to start here just with P1, so I'm actually going to erase this P2 for the moment, just kind of get it out of our way here. And I want to think about Biot-Savart, and we are given the Biot-Savart law here in vector form, and I'm just going to remind us that when we integrate, we're going to be using it in magnitude form. So let's write it out in magnitude form, mu naught I over 4 pi. And then considering the cross product, I have ds magnitude r multiplied by the sine of the angle between them over r cubed. And we can simplify that a little bit, but I just kind of wanted to put that out and remind us where that comes from there. And then, of course, we need to make sure that we feature phi in our diagram so that it's meaningful in some way. So it is time for me to choose a coordinate system here. And what I'm going to do is I'm actually going to take out this. We know this is r, that's given as r. I just want to probably write it in a different way. I want to write my axis here. I'll put my y-axis here, and let my x-axis be this horizontal axis. And I'm going to put my x equals 0 right here. I'll put my origin right here. So I just want to make it really clear that that's where my x equals 0 is. I'm going to put positive x to the right. I'll have positive y be upward. And then I'm remembering that this distance here was given to me as r, and that's a constant. So I'll write in my little ds. So my ds is it can put it anywhere, but I'm gonna go ahead and put it right here. And that's a little infinitesimal piece of current, right? A little current element, and I'm drawing it bigger so we can see it and kind of think about it. But mathematically, it's really small. And in this case, I'm gonna say that ds, little piece of length, I'm gonna call that dx since I'm on the x-axis. S is very general, and in order to make it meaningful, you need to customize it to your particular coordinate system. So it's not very meaningful if you always leave it at as S. The only time I use it as S is if I'm truly using it as a piece of arc length, where S is the appropriate notation for the arc length there. All right, so now I can pop in my R vector. R is always going to go from your current element, your source, right, to your point of interest. So here's my R vector. Looks like that. Remember, that's a vector. It has a direction. That's important. And the direction of ds, that's vector 2, is going to be in the direction of current. So that direction will be from left to right. The direction of current was given in this problem. I can now pop in my phi. Phi is the angle in between those two vectors. I usually use phi for something like this, where it's not a coordinate system angle. It's just an angle between two vector quantities in the problem. All right, so now let's go back and think about how we can rewrite some of this. My dB then is going to be mu naught I. That's a terrible mu naught. Let's make that a little cuter. So mu naught I over 4 pi. Sine phi, and then dx in place of ds, right, over r squared. And here I'm going to replace that r squared because I want to write it in terms of the problem. I remember that my x is going to be used in order to locate my current element, my differential element, with respect to the coordinate system. So this should really reflect back, this should make you remember the E-field problems that we did when we were doing the Coulomb's law E-field problems, because you used a lot of the same skills there. So x is going to be the distance here from my origin, my x equals 0, to where my current element is, where my differential element is. Again, x locates my differential element with respect to the coordinate system. R locates my differential element with respect to the point of interest. That's the same as it was for E. Meaningful, meaning wise, it's the same. Okay, so cool. What that means is that I have a way to define little r here. So I can say here where little r is equal to, now you can look at that right triangle there and see that you can write it as square root x squared plus big R squared. Now, we want that because if I have dx, right, I'm going to be integrating with respect to x, then I care about how x is changing as ds, as my differential element moves around, right? I'm going to say that again. I care about how x is changing as my differential element moves around. We're integrating because something's changing. If nothing was changing, we wouldn't even have to integrate. So we really want to keep our eye on the ball in order to describe adequately and as succinctly as possible exactly what's changing. Another thing that I can do here, I'm going to change up color in order to do this. Let's see, I'll use green, is notice the sine phi here. So let's rewrite that sine phi. Look at your right triangle there, right? Sine is opposite over hypotenuse. So that's just big R over little r. So sine phi is actually big R over x squared plus r squared. So that's going to simplify our dB. It's going to allow us to rewrite that dB. So I will do that here. I've got then my dB is going to be equal to mu naught I over 4 pi times r, big R, dx over x squared plus big R squared, all to the 3/2 power. Great. Now I just have to integrate that, and I have to decide what my bounds are going to be, right? So let's do that. We'll change for the most contrast, I'll change back to black here. So I'm finding my B, and notice that this dB doesn't have a hat on it, right? I'm in magnitude now. When I went from my vector form into the sine phi form, that was going from vector form into magnitude form. So that's what I'm doing now. And something we can do, like we can do at this point, is like pause and think about what's the direction of dB going to be. And that's probably something good for us to do right now anyway. Let me switch out my color though. So my dB is, I'm interested in the magnetic field up here at point P, right? P1. So if I'm considering what that is, I can do right-hand rule, ds. So however you do your right-hand rule, there are different ways to do this. ds crossed with r, right? That's going to give me a B field that is in what direction. So pause for a minute, do your ds crossing with r. And what you should find is you should find there a dB that's pointing out of the page. Sorry, that's supposed to be a dot. A dB that's pointing out of the page. You can also get that by using the other right-hand rule, where you have your thumb in the direction of current and your fingers curve in the direction of B. So you find that everywhere above the wire, in the page above the wire, the B field is coming out of the page, and everywhere below the wire, the B field is going into the page. Okay, so my point here is that we get our B field direction from right-hand rule. We don't get it from some equation. Okay, so rejoining our dB here. We can find our B just by adding up all the dBs for all the little segments, right? All the little dx segments on our wire. And that's what we do here. I'll pull out the constant stuff. So I have mu naught I r over 4 pi. I can put all that in front of my integral. Then I'm going to integrate the dx over x squared plus big R squared to the 3/2 power. And then I'm going to go from, notice where I put my x equals 0, so I need to consider that here. I'm going to go from negative L over 2 to positive L over 2. You may also go from 0 to L over 2 and then double that. That's also an approach that's fine for this problem. Okay, and then I would execute the integration and evaluation here. I have that in the written solutions. I'm going to kind of leave that alone for right now. What I end up with here for my B is going to be mu naught I over 2 pi big R times L over square root L squared plus 4R squared. And that will be, of course, coming out of the page. So that would be my full answer once I do my integration and evaluation for P1. And then I would encourage you to look at this. Once you see this, then you can think about what happens to this expression as L gets much, much greater than R. So you can do a couple things with it. But one is you can say what happens is the wire gets really, really, really long. And what that really means is that L is much, much greater than R, and kind of think about what would happen to the expression in that case.